Today we'll discuss about interpretable AI, which is understanding the AI systems, particularly a type of neural networks, convolutional neural networks, how we can make them understandable, how we can interpret the decisions made by them, etc. So yeah, at any point in time you can stop if you have any questions. All right. So we all know let us try to understand the basic motivation behind this research and this area. So machine learning and AI is there everywhere, right? So it is being used in healthcare, it is being used in
This conference
banking.
will now be recorded.
In healthcare, machine learning and AI is being used to diagnose, right? There are systems that that perform diagnostics like fMRI, starting from reading the X-rays and other scanning reports, and try to help the medical experts with diagnosing or suggesting a proper course of action, things like that. And in banking and finance also, there are a lot of automation is happening. For example, when customers apply for loans, and they give a lot of information about their financial career, right? How much they are earning, how many bank accounts they have, how many credit cards they have, how is the performance of their credit with their credit cards, and are there any loans, what is the age, what is the education, what is the geographical region he is living in, how much he is spending. All that information will be fed into an AI, and it will analyze the data given and decide whether to give the loan or not to give the loan, right? This is happening. This is not a story anymore. This is all happening in real world. And in law enforcement also, for example, in many of the courts in USA, for example, the prisoners apply for parole and early release, things like that, right? So they undergo a lot of interrogation. Of course, there will be some AI components that will take the application and analyze his crime records, age, everything, all the details, right? Everything it analyzes and tries to help the judges whether to give him parole or not. Let us say it can predict the probability that he will commit another crime if he is released, he or she, right? Such models are in action now. And in computer vision, we have been applying machine learning and AI extensively, and in speech processing also, right? I myself am using an Alexa, right? So there are a lot of such applications which are already in use. The people of iPhone users, they have Siri. You talk to the machine and it will identify what you're saying, and it will react to some of your requests also, right? And yeah, speech processing is another application front of AI where machine learning is extensively used in real life. And natural language processing is not very unknown to us. It is very familiar, right? A lot of language processing techniques are there in lot of institutions. In place of uh, human um, observers, there are machines that are, for example, customer care, right? Most of the simple queries in banks and other institutions are handled by machines. They understand what the person is chatting, and it will suggest the proper course of action to solve the problem, right? The machine NLP is also really right. All right. Yeah. So there are a lot of such applications in real life that are being extensively driven by machine learning and AI. So that makes us very, cautious. We need to really understand how the models are working, and when they predict what they predict, we should be able to understand why it predicted, why the machine predicted, why the algorithm predicted this way, why not the other way, right? Because machine learning is everywhere today. We need to go to the next level of completely understanding the behavior of the models, how they behave in a particular situation, right? All this is very important, particularly so in high stake applications like healthcare, banking, and in law enforcement, things like that, right? We all know how sensitive it can be. If we do a small mistake in medical diagnosis, right, it can be costly. Similarly, in banking and other applications like law enforcement, we need to really understand why we are doing what we are doing, right? If we completely trust the models, we may end up in unwanted situations. So we need to avoid all those unwanted behavior coming out of these models. So how to do that? We need to understand. We need to make them predictable. We need to completely dissect it, understand when it will predict what, things like that. So that is making models interpretable. That is interpreting the prediction of the models, right? That is in a way understanding the machine learning models, right? So you can think of it as a second step. The first step is developing the technology. Yes, we have developed it to some extent and now we are using it, right? When we are using, we need to understand whether we can trust them. Are there any situations we should not trust them? We should not go by their decision, and we have to overrule the decision and go by human decision, right? So these are some of the very active and very important areas we have to start with. Of course, we have to do this at all the application levels, but there are very high stake applications. For example, we are thinking about driverless cars. Can we trust driverless cars on the roads? Because if they don't really are intelligent, if they are not really intelligent, think of the catastrophe they can create, right? They can do chaos, right? So before we do that, we have to question whether we understand these models correctly. Do we know how they perform in a given situation, right? Whenever they take some action, do we understand it, why it has been taken, why not the other action, right? So this is what model understanding is, right? For example, I'll try to convince you with some very important applications why model understanding is very important and necessary. For example, think of a object recognition where the objective is to given an input image, you have to identify what is the object present in this. Let us say a classifier is trained, a predictive model or a classifier is trained to do a binary classification. It is already, which is being done actually. It's a real story. What I'm telling is a real story that is observed by scientists. So what they did is they trained a binary classifier, which is about classifying Siberian Husky versus wolf, right? So Siberian Husky and wolf, they look pretty close. One is a dog category, Husky is a dog category, wolf is a different animal, wolf, right? So they trained it, and the model is performing very good on the training data, and they took some testing data. There also the model is performing really good, so everybody is happy. Now they wanted to understand what features of the Siberian Husky the model is looking at to say it is a Husky, and what features of the wolf it is looking at to say it is a wolf. So they started looking at, and they came up with some models. So they investigated the behavior of the model. For example, in this case, so this is a Siberian Husky, and they looked at what regions in the dog it is looking at. Surprisingly, it is looking at the background, which is ice, right? This is snow. So it is very surprising and even shocking, because instead of learning the object category, object patterns, object features, the machine is looking at the ice. Whenever the photograph of Husky is taken in the training images, there is the snow. So instead of detecting or identifying the Siberian Husky, the model is only identifying the snow. Based on that, it is predicting it is a Husky, Siberian Husky, which is very, very dangerous, right? This is very surprising and even shocking. The model is expected to learn what makes this a Siberian Husky, whether these ears or the face or the fur. It should be something which is belonging to the Siberian Husky. Instead, the background information that is there in the photograph, that is being identified by the model to predict Husky. So this happened only because people started investigating or understanding the model. So this is something really a bug which is there in the model, right? This is kind of a model understanding leading to debugging the model. So unless we do model understanding, we don't know whether it is happening because the model understood the category or any other factor is influencing to classify. So this is one application. Model understanding leads to debugging. Also, let us take another application where this is a prisoner, and she's applying to judge for an early release or a parole, right? She has provided all the information. So we have trained a model already, and the model is given this data. And upon looking at the provided data, the model is predicting risky to release, right? The model thinks that it is very risky to release this particular prisoner. So we can stop her from getting released. But if we look at what factors the model is looking at to suggest that it is risky to release, why the model is saying, why it is saying, it is risky to release. So if you just look at the features in the input, in the file she has provided, so the model thinks because of the race and because of the gender, it feels the candidate is risky to release. But if you see, this is very discriminating. So the model should not look at these factors, race and gender. It is discriminating, right? So these are not very strong factors to suggest. It is in fact discriminating to rely on these factors to decide whether to release or not to release. It should be relying on the behavior, how the criminal behavior is associated with her, right? All that will be strong and more relevant features to rely on. But this model instead is relying on race, gender, etc. So that is why we say this model is not a reliable model. We should not follow the decisions made by this model. So then in these cases, the law enforcement would keep the model aside and go with the human decision. So here in this application, model understanding leads to bias detection because it is biased towards the particular race and its particular gender also, right? Which is not a healthy procedure. We should avoid biases, any biases, whether to gender, whether to race, whether to geographical region, whether to financial strength, things like that. So model understanding leads in this case to bias detection and correction also. All right, let us take one more application where this time an applicant is applying for a loan. So he will provide all the details, right? His education, his salary, his credit behavior, and his future plans, and all that he will provide. And there is a classifier whether it predicts based on the information provided whether it is profitable to give the loan or not profitable to give the loan. Let us say it said it has denied the loan. It feels the candidate should not be given the loan because it thinks that he would not be able to pay back the money. So in this case, the manager may directly go ahead and deny, or if he wants to know, if he or she wants to know what features in the application the predictive model is looking at. For example, so it will say what is lacking instead, right? So it has gone through the features, it has gone through the application, and there may be some lackings because of which the loan is denied, right? For example, increase your salary by 50,000 and pay credit card bills on time for the next 3 months. These are lacking. Your salary is lesser by 50,000 and you need to pay 3 more months continuously your credit card bills without missing. So then your application will be stronger and the loan will be sanctioned. So this kind of information should be given. It is very helpful for the candidate who applies, right? So this is not very straightforward. A lot of classifiers are not able to do this kind of a recourse, right? In this particular example, the model understanding is really helping to provide recourse. Recourse means some sort of help, some information to the applicant, to the input, where the input is lacking in order to be classified to other category, which is sanctioned loan, right? So this is all very, very important. This will happen only if we understand the model, what features in the input it is relying on, where the system is lacking. System is the application, where the application is lacking, right? So this is very, very important. In a whole lot of applications, this is required actually. So unless we do that, unless we have this information, we only think the predictive model, the classifier, is a black box. Something is going in and something is coming out, and no other transactions. It is not even explaining It will just take the input and give the output. So that way, its application is very limited, right? If you have this kind of an addition, it will make it complete. So this is what is intention of model understanding. This is also one of the applications which is very, very strong if we are able to understand the model, right? These are all the use cases of emphasizing the model understanding, importance of model understanding. All right, let us just summarize what model understanding can it enable and who will get benefited. As we have seen in the first application, it can help us in debugging the models, whether the model is relying on the right features or it is just looking at the um, unwanted, not unreliable features in the input. So this is very, very important. So we cannot directly deploy the model unless we understand it is doing the reliable job or not. So all the end users will be the benefited from this debugging application. In the second application, we have seen bias detection, whether the model is biased to some race, some gender, some economical category. So these are all some of the very, very important factors. Otherwise, if we don't identify them, the decision makers will be doing a bad job, right? So if they understand it correctly, they can correct the mistakes or whatever the lackings in the system, right? So because of this, decision makers like doctors and judges will be like the first people to get benefited because of this application. And we have seen in the third application.
Sir, I got a question. In bias detection, how the biasing, you said bias, it need not be also, correct?
Correct. It need not be also, but it depends on the data set on which it is trained. So we have to make sure the data set is.
When we train, we normally train both the cases, correct? In worst case as well as in worst case scenario also we'll be training it in order to make the prediction. So in such cases, whether it is biased, that's what I'm asking.
Right. So it is not very easy to ensure unbiased data sets, right? If you gather a lot of data which is available, and it often is very, very difficult. For example, organizations like Facebook and Google and Microsoft, they do have hell lot of data, millions and billions of data. So it is very difficult to manually verify whether the data is biased or not, right? So unknowingly, we may sometimes don't know that a bias is creeping in the data, right? Unless we do diagnosis like this, we cannot find out. So there are no direct ways also to find out biases. Of course, to some extent we can avoid. For example, add as much variety. Like make sure you have male candidates, female candidates. Make sure you have all age groups, all races, all financial backgrounds. This is to some extent it is possible, but in applications where it is not possible, the other way is to do the postmortem. After you train the model, you can do also. What you said is correct, sir. In general, we try to do as much care, as much diligent work in data collection as possible, but more often it is not the case because of the scale of the data.
Okay, fine, sir. Thank you.
No problem. Yeah. So because of the records meaning the application where the model said where the applicant is lacking, what he has to improve in order to get the loan sanctioned. So this is very, very helpful for actually end users actually. Yeah. So yeah, end users means the people who are getting benefited from the models. And other application is vetting models to assess whether it is suitable for deployment or not, right? Whether we are ready to deploy it or not. For example, if you identify some biases, we will not be able to put them into deployment, right? Biases or any bugs like this, we will not be able to put them. So as machine learning developers and researchers, we have to do, once we develop a model, we have to understand whether it is functioning correctly, whether it has learned what we want it to learn, or is it cheating by learning some bugs in the data like this. So this is all very, very important, given that as of now, we are already using a lot of machine learning and AI in our lives. In future, it is expected that a lot more of our tasks will be helped or done by machines, right? These examples is a pretty good scenario how well we are depending on machine learning and AI these days, and it will only increase in future, right? So we are expecting that all the warehouses will be deployed by robots, not just the humans anymore, right? So that is the first starting point, basically to replace humans, right? Wherever things are pretty not intelligent, for example, it is only a predefined set of tasks we need to do. We can employ the models, and with minimal intelligence they can get over with that. So starting from there, a lot more of applications will be handled by computers. The AI will drive some of these applications. So we need to be really, really confident. We need to trust them. Only then we can deploy. Otherwise, it will not go according to the plan. All right. It's all understood. Now we understood, yes, it is very important to understand the model behavior. Otherwise, a lot of problems will occur. Now, how to achieve model understanding? How do we understand? How do we actually, make the model's decisions interpretable, right? So let us see. So one way to achieve model understanding is build inherently interpretable models. The models which are simple, which are very easy in the sense we know what is happening. So in that case, for example, linear models like linear regression, logistic regression, things like that, they are pretty simple. So we know what is happening. We are learning a line. Everything, we are trying to fit a line to the data in this linear regression application. So how much we need to increase X to get a specific increment in Y, we know, because Y is equal to mx plus C. 1 unit increment in X will cause m units increment in Y, right? So for example, let us say this is an application where the line is between amount spent on advertising and the increase in the product. Let us say one of the product companies is trying to understand how much it is investing in TV advertising so that the product sales will increase, right? If you fit a model from the training data, historical training data of the company, we can find out if I increase 1,000 US dollars in TV advertising, it will increase by how much my sales. So these things are very easily understandable in linear models. I think if some of you might have already attended my session on linear models, linear regression and logistic regression. So that application we dealt there. Once we learned the model, the M will tell us that slope. 1 unit in increment in X will cause M units increment in Y, things like that. So that way, to some extent, linear models are interpretable because of the simplicity. We know everything, what is happening in the model. Because of that, even shallow decision trees also like that. So for example, take this very simple decision tree where everything is pretty clear. If age is between 18 and 20 and the candidate is male, then predict yes. So we know what factors are making the prediction yes, what factors are making it no. So because the model construction itself like that, because of that, it is very, very easy to interpret these models, right? This is one way to achieve model understanding. Try to build the models that are inherently interpretable. And second way is, let us say there are very complex models, very, very sophisticated models like deep neural networks, for example. So we need to, once you learn them, which are like black boxes, we don't know what is happening. There are layers, there are transformations, non-linearities, dropouts, batch norms, lot of complicated stuff is there, and it is doing a very good job. And we don't know exactly what it is learning, how it is predicting. So these factors are not known because of the complexity, because of the sophistication that is put into these machine learning models, right? So in those cases, what we can do, we can devise methods to explain the behavior. So independent of the training, we have to again invent some methods to explain their behavior. So let us say there is a method, there is an algorithm which takes this model as input and tries to give some explanations in terms of simpler models or in terms of a lot of other ways it can explain away, right? It can give you where it fails. It can give you where it feels comfortable. things like that. So we'll come to in the future slides, we'll come to see what makes an explanation, what is a good explanation. All that we will come to see. So this is the second method. The first method is go with the simple and easy to understand methods, or in case of second sophisticated models, what you need to do is you need to invent some more methods to make them interpretable. All right. So when to go for what? There are two methods. When to go for what? So the decision is simple. Some cases, there is a trade-off between accuracy and interpretability. So if your interpretability is high, your accuracy is low. If your interpretability is less, the accuracy is high, right? That means it depends. If you want more accuracy, the methods will suffer from interpretability. They cannot be interpreted easily. For example, DNNs, deep neural networks, they perform very good. Accuracy is very high, but they are not very interpretable, right? On the other hand, take the linear examples, the linear regression, logistic regression. Accuracy is very small, but you know everything about them. Interpretability, they score very high. Because, as I said, we know what is happening, what inputs they are taking, how they are getting multiplied, and how the prediction is coming. All those things are clear. And similarly, decision trees also. Accuracy may be small, but interpretability, you know everything about the model, how it is taking the input, how it is classifying, all the branches, how it is clearly defined. So this interpretability, because of this, we need to keep that in mind. For example, yeah, this is one example where you can see where models fall. Linear regression, interpretability is high, but accuracy is low. On the other hand, neural networks, accuracy is very high, interpretability is very low. And there are models like decision trees, random forests, where they fall in between. So this is generally observable because these models are simple, linear regression and decision trees. The accuracy may not be high. So the gist is, when the model, when the problem is simpler, when the data set you are analyzing, when the problem itself is relatively simpler, and if you are confident that you can build interpretable models that give good accuracy, then go for it. For example, this is a very simple data set. It's a linearly separable data set where the two classes are very closely separable by a line. It's not very complex decision boundary, right? It's a simple line that can separate both the classes. So in this case, simple models like linear classifiers will work because the data set itself is not very complicated. So in these cases, we should go for interpretable models, simpler models. But in some cases, the classification boundary will be very complicated. Here, the orange space is one category and the blue space is another category, right? So we cannot clearly separate the two with a simple line. The decision boundary is very complex. It's not even a regular shape. It's a very irregular shape. So for learning these kind of decision boundaries, you need sophisticated models like deep neural networks. So in this case, if the problem is very complicated like this, we should go for the sophisticated models, and then different explaining algorithms have to be used on top of these methods. So this is the rule. If the data set is simple, you think that the linear models are good enough to use it because they are interpretable. But if the problem is very complicated, the decision surface is not very simple, you have to go for very complicated models like deep neural networks, and then on top of it, you have to use methods to interpret. We will see one or two such methods also. So this is how we should select what method to use, right? So the second case where we use sophisticated methods to train the classification, and then on top of it we use the explanations. They are called post hoc explanations because they are happening post learning, right? Once you train the model, you are coming up with another method to interpret the model. So because of that, it's called post hoc. It's after the training is done, after the classifier is independently trained to perform high accuracy, right? All right, so that is how one yes. So what we mean is basically if you use the second way, which is training very sophisticated classifiers, and then on top of it we use the another algorithm to explain the behavior, because this is not part of the classifier training. This explaining behavior, which is an algorithm, is taking the classifier as input, right? This is already trained classifier. That is why this kind of approach is called post hoc interpreting, because it is happening after the classifier is trained. If you take this model where the simpler models, there is no new algorithm which is trying to explain. The classifier itself can do explanations, right? All the questions we have seen in the linear regression case, it is answerable because the model itself is answering. There is no another explainer, another algorithm is not required, right? That is the difference. In this case, it is called post hoc because after the classifier is trained, you are now devising another method to explain the classifier. All right. So this is when this is how to decide when to go for what, right? So this is the summary. If you can build an interpretable model with adequate accuracy, you should go for it. Otherwise, resort to post hoc explanations for the complex models, right? So this you should keep in mind, particularly in applications like what we have discussed. If you are working, if any of you are working or doing projects in those areas, you should think, if the problem is relatively simpler and we need explanation, go for simple models like the shallow decision trees or even linear models. You can go for it, and it will answer a lot of your questions. You can ask and get answers. And if the problem is complicated, the data set may be too complex, in the sense a lot of dependencies and a lot of variety in the data, things like that. If they are there, go for a complex classifier like DNNs, SVMs, things like that. Okay, and then you have to look for ad hoc explanations also, because these applications are like that. We need to build the trust. So without trusting them, we cannot deploy the models in real life. So that is how one should decide on which model to use. All right. So in this remaining session, what we'll do is basically we'll see some of the only post hoc explanations, because the other ones, which are simple models, they themselves can answer, right? For example, if you see, yeah, so let me just quickly revisit. So here the explanation is pretty much evident, right? So what features it is dependent to say yes, what features it is dependent to say no, or if it is getting no, because of which factors it is getting a no, where the input should be improved or changed to get an S. All these things, by the nature, by the construction of this classifier itself, you can know, right? So they don't need extra algorithms to explain, right? Here also, most of the questions are answered in the method itself. That is why they don't require ad hoc, post hoc, right? So this is where post hoc is required, where the model is complicated, like neural networks. So today, most of us are using neural networks. Deep learning is there, dominating in every application, right? As I said, some of these applications I have showed to you, I think most of them are driven. Most of the state-of-the-art classifiers in those applications are driven by deep neural networks. For example, I'm pretty sure, I know confidently that computer vision, NLP, speech processing, all the companies are using neural networks. For example, some of these handheld devices like phones, they have face recognition, right? Um, which is driven by neural networks, right? So a lot of phones these days are advertising the face recognition algorithm used by the phones is driven by neural networks, right? So this is there everywhere. Almost all the applications are now driven by neural networks. Particularly because I've been working in computer vision, I'll try to give you some applications from computer vision where how we can explain the classifiers trained in computer vision. After you train them, how do we ask questions? What are you looking at? Why you are predicting this? Why not that? All these things, how we can do. Okay. So please bear in mind, although we are discussing computer vision applications, they are pretty generalizable to other applications like NLP and speech processing also. Only the data is different, but the models, training procedure, the classifier building, everything is same, right? So that way, these are pretty generalizable. Okay. So let us try to understand more about explanations. So what is really an explanation? So some of you might be really thinking, it is clear but not entirely clear, right? What is an explanation? If you ask a human being to explain, he will explain in language, right? In English or Telugu or whatever language he's comfortable in. He'll try to explain why he reacted in a particular way in a given situation, how he reacted, or he or she, how they reacted. They'll clearly explain. See, because of this, I chose this action. So I wanted to do that, but because there was something lacking, I could not do that. So that is an explanation, right? But in case of classifiers, what makes an explanation? So by definition, explanation is any interpretable description for the model behavior. So anything that can be understood by end users like us, humans, right? Anything which can be interpreted by us, any description of the behavior. So this is by definition an explanation. For example, there will be a classifier on the one side. There will be a user on the other side. So explanation. So this is what is, right. These two are the entities that are interacting. The user is applying some input to the classifier, and the classifier is spitting out its classification, the label, the decision made by the classifier. So explanation is in between. It should make the classifier's decision understandable by the user. So whatever the classifier says, it has to kind of translate to the user so that he understands. So it has to be faithful, because the explanation should not tell something other than something which is not done by the classifier, right? Whatever is classifier doing, exactly it should be conveyed to the user. It should not be something other, something which is deviated from what the classifier is doing, right? It should be faithful. That way, the explanation should rightly bring out the behavior of the classifier. And at the same time, it should be understandable also. It cannot cater something that is difficult to understand by the end users, right? So why we are focusing this much on the definition is because the variety of explanations that are possible is huge. You will see, you will see what makes an explanation just in one or two slides only. So we need to understand what should be an explanation, right? Because there will be a variety of systems based on the application. The explanation may vary, right? So just try to relate to the applications we have discussed. So in every application, the decision is different, the relying factors are different, although there is a common underlying thing, which is explaining the behavior of the classifier. So that is what an explanation is. Let us say, send all the model parameters. As an explanation, the classifier will give you all the parameters of the model. For example, in linear classifier, y is equal to mx plus c, there are two parameters, m and c. So if it gives m and c, to some extent, the model's behavior is understood, right? So for example, if I say m is equal to 10, if I increase by 1 unit the x-axis, the y-axis is going to increase by 10 units. So that is some information, some explanation. So if I want to see 100 growth in my y, I need to increase x by 10. So that is to some extent, that is an explanation, right? It is answering some of the questions. It can be useful by the user. All right, that is one explanation. And send many example predictions. Okay, I'll repeat. So sending all the model parameters, is it an explanation or not? So in case of linear regression and logistic regression, things like that, if the model gives away the parameters m and c to the user can understand some information, right? What information? How much he needs to increase x to get a particular increase in y, right? So as I explained, if m is equal to 10, if we change x by 1 unit, the y will be changed by 10 units, right? So here the model parameters are conveying some information. For example, the user wants to increase the y by 100 units. Because m is equal to 10, he needs to increase the x only by 10. So that mx 10 into 10 will increase the y by 100, right? So some of the behavior, model behavior is being understood. So this is one way of explaining the classifier, which is sending all the model parameters. But in case of complex classifiers like convolutional neural networks or any other deep neural networks, there will be millions of parameters. We cannot do anything with them. So there it fails to be a proper explanation because it is not easily understood by the user. Because of that, this is only, some models, it can act as an explanation, but not all models. I hope you see why, model parameters, in case of CNNs and DNNs, very, very complex models, there will be millions of parameters. I'll just, throw a million parameters at you, million numbers at you. You will not be able to understand. You will not be able to go through them also, first of all, right? So those cases, this is not a very good explanation of the model. All right. So how about sending many example predictions? For example, as an explanation, I'll tell you, so for all these examples, this is what I predicted. Yes, this is some explanation, right? You will see, 100 example inputs and corresponding outputs. That will tell something about the model, right? But not a great deal. You will still have a lot of questions unanswered. You will have a limited idea, some idea, some basic idea about the classifier, what it is predicting, because you saw 100 examples. Now think of looking at 100 instances where the classifier is applied, but you will have some idea in the 101st case, right? How the classifier will behave, because you already have seen 100. So things like that. This is also some explanation. How about summarizing with a program or a rule? Yes, this is an explanation. For example, if you see the shallow decision tree, here the program behavior is summarized in a set of rules. If else rules are just characterizing the model behavior. This itself is an explanation. So this is an example explanation. All right. How about selecting most important features or points? Yes, that is also to some extent it will explain, but not all the explanation. Right? Important features meaning in the input, what components it is relying on, what input quantities the classifier is strongly looking at. So this is some explanation. Or important points in the training data. For example, you have some 10,000 training data, out of which some points are found to be really important by the classifier. Model's behavior is strongly dependent on them. If you just show them, that also tells you about the model's behavior, right? How about describe how to flip the model prediction? So as an explanation, we can tell how to flip the model's prediction. So what I should change for making it the other label. For example, one of the labels predicted is yes. What should be changed in the input to predict yes, no from yes, right? So this is also some explanation. Okay, so in order to flip the prediction, this is what to be changed in the input, or this parameter of the model should be changed, increased or decreased, things like that. So these are all different explanations, different possible explanations for the model. So that way there can be many such explanations, right? Whatever interpretable description about the model behavior we can think of, it becomes an explanation, right? So these are generic concepts. I hope you see what we mean by explanation. So these are all, as I said, the diversity of the applications, diversity of the data, diversity of the user levels that are being used in the picture of this whole machine learning. The variety of explanations is also very diverse, starting from model parameters to all the way, what changes we need to do in the input for making the model prediction change. So what I'm trying to say is it is very vast area. It is although the fundamentals that are driving are simple. What we want to know here is model behavior, how the model behaves. That is what we want to know in every application. But based on the application, the explanation may change. All right. So these are all different possible explanations for the model understanding. All right. So there are more There seems to be a question. Just hold on. I missed the question. Yes, is explanation an interface? Yes, you can think of an interface, because you're interfering with the classifier so that you will get some understanding, some answers to your questions. So that way it is in an interface through which you are trying to know the behavior of the classifier. You can think of that way. Yes. Basically, it is an algorithm, or it is a set of instructions which interacts with classifier and brings out some information to the user, so that he feels happy about learning something about the behavior. So that is what an explanation is. We will see some of these things. All right. So there are broadly two kinds of explanations also: local explanation versus global explanation. Again, this is not a hard classification. Based on the nature of the explanation, we can think of them as local versus global. So what is global explanation? Global explanation is basically which characterizes the classifier altogether. So when I say a particular CNN, so how it performs, what it learns, what is the input features it is depending on in general, right? So that's global. The characterization is done at a very high level. For example, if you see this classifier, so this is a global explanation. So these regions it is classifying as orange class, and all the rest of the regions it is classifying as the blue class. So this is one explanation. So if you understand, if your input is only two-dimensional, this is origin and this is x-axis and this y-axis, you know which regions in the 2D is blue class, which regions in the 2D picture is orange class. So this is a global explanation. But if you want local explanation, so whatever point you are looking at, for example, you have a very specific point, let us say 1,1, around which you want to understand the model behavior. So this is, you want to only concentrate on this local area, not the global picture. So that is also possible. Sometimes, there will be, think of a medical diagnosis case, right? So one particular patient, doctors are analyzing.
Sir, I got a question. Sir, local explanation, you're given and global. See, the picture shows it's an M for Mopuri, correct? It's an M actually written, correct?
It's not written in that way. Yes, you can think of that way. This is a data labeled one class in this region, and the rest of it is another class. Yes, you can think of that way. Yeah.
So whether it is a globally you can think of, but locally, I didn't understand the difference between what you are saying between local and global. Can you explain it again once more?
Yeah. So global explanation of a classifier is, it's a bigger picture. For example, think of a classifier which is okay. So you remember the class? Okay, let me just take you there. Here. So this classifier, after analyzing by giving different inputs and finding out what it is looking at, the global behavior is this. The classifier is looking at the snow present in the input images to classify it as a husky. If there is snow, it will classify as husky. If there is no snow, it will classify as wolf. That is a global explanation. So which is characterizing the classifier altogether. It is not dependent on this particular image. For every image, the behavior is like this. If there is snow, the classifier will predict husky. If there is no snow, it will predict a wolf. So that characterization, that explanation is global, right? So it is not dependent on any particular input. It will hold for every input. Whatever explanation provided, it is true for all the input. That way it is global. For example, on the other side, take one particular point, one particular data. So here, let us say you want to talk about this particular input. Let's say 1,1. So you just zoom in. Just look at surrounding regions of this data. So what you can say, within the surroundings of this data, it is simple linear classifier, right? The behavior altogether changed. It is no way a linear classifier. It is very complex classifier. But if you zoom in only within the neighborhood of this particular point, it simply becomes a linear classifier. So in this region, even a smaller, simpler linear classifier will be good enough, right? So that is a local explanation. This explanation will not hold in any other regions. This explanation will hold only within this region. Is it clear, sir?
Got it.
Yes, yes. Yeah, so that
Thank
is
you.
sometimes, yeah, no problem. So sometimes it is required because there will be so another example. Yeah, so it depends. Basically, it depends. The local explanations depend particularly on the input. For example, if you just go to another interesting point, it may not be the case. So all these points, it is local in this region. It is local classifier, right? But sorry, it is linear classifier. It may not be the case. For example, if you take this corner point, it is not a linear classifier, right? So you cannot have a line which separates the orange class versus the blue class. So it just happened that it's an interesting point where within the surroundings of this point, a linear classifier will also be good enough, or the classifier behaves like a linear classifier, right? So that way, sometimes it is required to have local explanations. For example, take very high stake applications like medical diagnosis, right? So if you are particularly analyzing uh, patients of age 30 uh, who are female and also coming from the South India, right? You restricted a lot. So within the bigger picture, you just restricted. You restricted the age, you restricted the gender, you restricted the geographical region. Then the classifier may be a different altogether, right? In those cases, these local explanations will be required, right? Because sometimes we do a lot of data analysis. So there will be a lot of questions they want to understand. For example, policymakers or even the developers ourselves, we want to understand how the data is, how for example, take the COVID cases, right? How the COVID is affecting different age groups, different regions. So a lot of analysis can be performed, which can be used for in future, or just to analyze also. So all those cases, local explanations do help a lot. But on the other hand, global explanation will try to characterize the whole bigger picture. How the classifier, is it learning reliably, or like that cheating classifier, is it only learning some background information and getting away, instead of learning the actual dog category and the wolf category? What makes a dog, what makes a wolf is what is intended, but instead it is cheating. It is just trying to find out something which will improve the classifier accuracy. It is working, but it is not correct. All right. So that's about local and global. So you can compare. So local explanations basically explain individual predictions, as we have seen, but the global explain complete behavior of the model as a whole, how it performs. Again, local explanations discover biases in local neighborhood of a given sample. Local neighborhood, which is very restricted area, right? But on the other side, bigger pictures, bigger biases that are affecting the model will be brought out by the global explanations. Similarly, everything that happens within a neighborhood of a particular sample, that is resulted by the local explanation. The global explanation tries to give you on a bigger picture, bigger scale, general behavior it will bring out. So based on the application, based on the necessity, sometimes you want to analyze local things, sometimes you want to understand broadly. So we have to pick based on our necessity, based on the application, based on the questions we want to answer. You have to pick either the local or the global explanation, right? And also, if you go on increasing the neighborhood of the local, it will become global, right? If you see, this is right. So if you just think of zooming out from here, you will reach this picture, right? So it depends. So to what neighborhood you want to understand. For example, are you just looking at age 30, or plus or minus 5 years is also okay? Things like that. So as you go on loosening the neighborhood, it will become a global explanation, right? All right, so it's a big spectrum actually. So it's a continuous spectrum. It's not like clear separation is there between global and local explanations, right? So all these local explanations can also become, all global explanations can become local if you restrict the neighborhood and all that. All right. Okay, so that's broadly about explanations. So I'll just try to recap what we have seen. So we have understood that machine learning is there everywhere. We cannot blindly trust them. We have to understand whether they are relying on the right features, right information, or they are just cheating us with bugs in the training. So there are a lot of applications. We can provide recourses to the users, what they can improve to get positive outcomes, favorable outcomes, right? Whether there are biases towards any gender, towards any race, towards any geographical region, you can find out whether the models are biased, right? Whether they are predicting correctly, all these things you have to understand before you deploy the model. So that is where model understanding comes, right? We need interpretable methods. What is an explanation? Anything that tells us the behavior of the model. It can be the parameters of the model. It can be the important features it is relying on. It can be the important training data which are which are used for training the model. It can be the changes in the input that should be done to make the model's prediction to be flipped. So anything that makes some behavior understandable is an explanation. So there are categories like local and global. If you are restricting the model behavior within the neighborhood of a data point, it is called a local explanation. But on the other hand, if you are looking at the bigger picture, if you want to generally understand not just one data sample, it is called a global explanation, right? So now we'll try to see some applications in computer vision, some explanations in computer vision. So I hope you understand computer vision. Basically, not entire computer vision, only object recognition. So object recognition, what it means is, let me just show it to you. So there will be a classifier. What it should do is take the input image and predict the label. This is a cat and this is an elephant. It has to just predict y from x. It's a classifier, right? It's a classifier which predicts y looking at x, right? So that's object recognition. It is recognizing object which is present in the input image. So there will be, let us say, 1,000 categories from which it will pick: dog, cat, elephant, laptop, pen, paper, phone. So all these things, everything that we come across in daily life, you can think of it as a label, and it has to predict the right label. That is object recognition task. All right. So I'll try to introduce you to convolutional neural networks. So think of it as a neural network which is operating in 2D data. So 2D data like image, video, these are all, it is not a speech, right? Speech is 1D data. And on the other hand, image is XY axis is there, pixels are there. That is why it is 2D data. It operates on 2D data and predicts the label. So this is one of the, or like the most successful computer vision model in recent times. So almost all the object recognition is done by neural networks now, the deep learning. So deep learning is subset of machine learning that uses neural network. Okay, so it is not different from machine learning. It is very much part of the machine learning only that neural networks or regressor, whatever model you are training, it is trained by neural networks. Then it is called deep learning. All right. So CNNs is a very strong component of the deep learning. So they are using beyond computer vision actually. So even in speech, they use CNNs. Even in audio, NLP, they can use CNNs. That is why it is one of the successful models. Okay, but they have very complex parameters. They have millions of parameters, hundreds of layers, and millions of the weights. Weights means parameters that join the layer between successive layers actually. So because of that, they are considered to be black boxes, right? Black boxes means, what they learn is not known. How they are predicting is not known. Only they take millions of data and labels and they do backpropagation. They train over hours and hours time and they are ready to predict, right? like the linear classifiers or the shallow decision trees, they don't explain why they are predicting what they are predicting, right? They simply take input and spit out the output. So that is the reason most of us think like they are black boxes. Not relatively less now, but initially when they were introduced in 2012, up until 5-6 years, people were not very welcoming. Like some people did, but not a whole lot of community were happy with it, because most of it was like training with thousands of images. We know only X and Y and nothing we know. It's just back propagation and error minimization and parameter updation. So people were not very happy. They were thinking it's a black box and it will not be successful, it will go down in time. But surprisingly, it has won over all the competitions. All the applications are driven by CNNs, and most of the opposing community also changed their opinion and started using CNNs. So this is what I think is true. Yeah. Anyway, so because of that complexity and the structure of the CNNs, most of us started to think about CNNs as black boxes. They simply take input and give output. But what is happening inside, nobody knows. But people started, looking into and framing, devising methods to explain the behavior. Slowly, it became, transparent. So it became to explain things away. So let us see some of those um, explanation methods also. But before that, a brief set of points I can say to understand why it is important. Because lack of decomposability makes it difficult to interpret. Lack of decomposability means we cannot, for example, think of this shallow decision trees where it just asked what is the age of the candidate, what is the sex of the candidate, what is the other feature. So it's very clearly decomposable. The features are being processed independently, and at any point in time you know what is happening. But in CNN's case, it is not like that. The entire data goes in, and the processing happens from top left corner to bottom right corner uniformly. There is no difference in applying any transformations. Everything will be treated uniformly, and directly the label comes out. So that there is no much of decomposability. Because of that, there was no transparency also. When they fail, there is no warning, there is no explanation. For example, if it misclassifies as a laptop, we don't know. It doesn't tell why it failed, or it doesn't even realize it failed most often. But even then, it doesn't say any useful information, whether it failed, whether it succeeded, even if in both the cases why it did what it did, nothing, right? And we have seen the graph, right, between the accuracy and interpretability. These models are very strong on accuracy, but very poor on interpretability. So in applications where interpretability is important, these models are not useful, although they have very good accuracy, right? So because of that, people started thinking we cannot afford to not use because they don't have interpretability, right? See, since they have very high accuracy, we should work on the interpretability so that we can use these models everywhere. So this is the primary motivation. Accuracy is there. So if we can work on the interpretability aspect, this was a drawback. Let us try to work on this aspect so that CNNs can be used everywhere, right? Think of a cancer diagnosis. So a lot of MRI scans and a lot of other data will be converted into images, and they train CNNs. A lot of hospitals are working with data scientists and machine learning engineers to develop automatic tools that will do the diagnosis, of course in the presence of surgeons only. But see, the computers can see patterns that are not easy to see by humans, right? For example, they can perform face recognition with low light, night light, and very poor resolution. Humans, although we are more intelligent, we cannot perform such difficult tasks, right? Similarly, medical diagnosis data is also very, very difficult to interpret with humans. So there will be subtle patterns, subtle information that can be identified by the computers when you provide a lot of training data. So that is what is happening. in a lot of these applications. They're trying to work on the interpretability aspect. So let us see. So what do we need to explain here? We need some sort of reasoning for the prediction. Reasoning in the sense, because these are dumb models, right? They cannot tell you why they predicted. So we need some explanation, some reasoning. As I was saying, right, humans, they can explain in the language, whatever we speak, why they behaved in a particular way in a given situation, right? So something like that we need for the CNNs also, so that the users could relate the input and the predicted output. Oh, okay, because of this you predicted this. Okay, it makes sense. Or when it fails, if there is an explanation, the user can see, oh, because of this you thought this is a dog, but not, it is not general, it is not a dog. Because of these features, you seem to be confused, but it is not actually dog. Now you can go back and work out on those shortcomings of the model. So these are all lot of explanations possible. All right, think of this. Now enough of explanation. Let us look at this diagram. Let's say this is the input image. The label predicted is bird. So it is pretty simple. We can understand. But think of a very complex, input like a medical diagnosis, where because of some of these regions, it will say there is cancer, there is no cancer, things like that. So if you have the model identifying the pixels which have influenced the model to predict it is a bird, then it is better, right? Instead of simply saying it's a bird, along with saying the bird, it can show these regions. See these pixels, because of these pixels, I think it is a bird. And similarly, because of these pixels, I think there is a deer in the image. It is more, right? It is explaining, it is reasoning why it predicted bird in this case, why it predicted deer in this case. But generally, the classifiers are not trained using that, right? How we trained them? We said this is a dog, this is an elephant. We did not say this is particularly the cat, this is elephant. We did not say that, right? We said the label for this image is elephant, the label for this is cat. But despite that, the model is now telling what regions in the input are influencing what, because of what reasons it is saying it is a bird. Here also, it is very, very clear, right? Now there is no doubt at all, because the model is looking at these regions and highlighting them and telling that there is a deer. It is very clear. It's a reason, right? So these are called visual explanations. So this is coming as a byproduct. This is not being trained. All that we trained for is predicting the right label. When I say this, it should say cat. When I show this, it should say elephant. That's it. But along with saying elephant, it is even identifying the pixels of the elephant. So that is explanation. So this is very, very encouraging. This is very required also. And when it fails, I'll show some examples. When the classifier fails, it will also say, because of these regions, I predicted this. Now we can understand, right? Yeah, so these are all these examples. I'll take some more time to explain. Before that, let's do. So there are a lot of ways, even in CNN visualizations, there are multiple ways to actually go about. For example, we can take one neuron and try to understand what it is understanding, what it is detecting in the input image. And evidence localization is something like this. So you said there is a bird. Can you localize the evidence for bird? Yes, the model will say, this is my evidence for bird. This is my evidence for deer. So this is evidence localization. And feature reconstruction means, you can give a feature and ask it to reconstruct how it looks in the input space, right? You can give an output vector and try to find out what the input looks like, corresponding input looks like, right? All right, let us quickly see neuron visualization. So this requires a bit of CNN understanding, but I'll try to minimize as much as possible so that you will easily understand what this works is about. So each row corresponds to a particular set of inputs that fired one neuron, right? So this is a neuron, let us say in the 5th layer or 6th layer of the neural network. So they wanted to see what set of inputs fire that particular neuron. Fire means, the neuron activation is high, right? So it clearly says all humans, it is detecting humans, right? So it is kind of a human label classifier or human object identifier. So if you can relate this to the human or any mammal brain also, there are specific regions in our brain that responds to specific stimuli, right? So there are responsible regions, for example, for performing mathematics or logical thinking, there is some brain region that is responsible. For arts like music, there is a different region that is responsible, right? So for vision, there is a different region that is responsible. For smelling, there is a different region in the brain that is responsible. Similarly, in this neural network also, for identifying the human objects, there is one neuron. Similarly, the dog objects, there is one neuron. There is a house objects, there is one neuron. Things like that. There is a neuron that is firing for text. So the numbers and text on the walls, right? So this is another neuron. Things like that. So flashy objects, light or polished objects where the light is reflecting. So some neurons in the neural network are firing, right? So this is explaining that neuron via examples, right? So you remember one of the explanations was, let me just take it, here. So send many examples as predictions, right? So that is one explanation for one of the neurons. So this one neuron, which is activating for this whole row, right? You can understand. Now you can explain, okay, this particular neuron will fire when there is a flashy object in the input. This neuron fires when there is a house object in the input. Similarly, a dog object or a flower object, things like that. So this is one way to explain stuff. What do the numbers represent in this example? Yes, so the activation. So the neuron will have the output, right? So if it is there is a sigmoid output on the neuron, the maximum value will be 1 and the minimum value will be 0, right? So this is the activation that is present in the corner. So when this input is present, the maximum output is achieved by the neuron, and it's close to 1.91, things like that. So 0.7 here. So this is some set of examples that are firing with high activation. All right. So this is one explanation. So there are other explanations also possible, like so I'll just skip. What it does is basically you have to invert. So let me just take you through. So in the normal operation, it is feed forwarding, right? You take the input image and then you go towards the label. But they have come up with an interpretable algorithm which comes backwards and tries to reconstruct the activations. They look like this actually. So when you come from second layer, they look like this. When you come from fourth and fifth layer, they look like this. So what they found out is when you go deeper, what the neurons learn is objects. When you go, earlier layers like second and third, you will find edges, combination of edges, parts of objects, slowly objects all together, right? So this is where you see edges and blobs, right? This is a second layer. And towards third, fourth, fifth, you will find, the objects themselves, the dog objects. You can see dog faces themselves. So that neuron is learning the dog category altogether. So this is based on neuron visualization. You can explain the behavior of the convolutional neural network that is performing object recognition. So evidence localization is more familiar and easy to explain also. So what is happening is, for example, this is the input image. It predicts as a ship as the label, and now highlights the regions in the input image that are responsible for the prediction. So now it is clear, right? The model is saying it is ship, and it is also saying because of these pixels, I am saying there is a ship, which is good. Think of this in a medical diagnosis. It will predict cancer and show in the input because of what pixels it is showing there is a cancer. So it is easy for the surgeons to look at those regions and understand the situation better, right? So it has an immense value actually, not only in the commercial object recognition, but in medical diagnosis. And sometimes, the CNNs are used in other fields, astrophysics, right? Where high dimensional um, input images, which are of sky and the space, right? They are not very easy for humans to read, but the machines, they can read, they can identify what objects are there, and you can locate actually, which is very, very important. So these are image specific visualizations. So these are local explanations, because this explanation is only for this image, and so on. So these are also very, very, there are a lot of ways you can come up with. So I'm not going into the technical details, but the objective is to come up with regions in the input image that influence the classifier to predict the label. For example, here also, the model is predicting barbell, and it is clearly locating, because of these pixels, I am saying it is a barbell, which is correct. Here also, because of this and this, see here, these regions are highlighted, this region and this region. Here also, this region and this region. It is relying on these regions to say there is a barbell in this image, which is very good actually. It can just say barbell, but it is instead saying, explaining also. So because of these pixels, I'm saying barbell. So we also worked actually when I was doing my PhD at IISc. So we also presented a novel method to do this. So from the label, which is monkey, we can backtrack all the way and find out the pixels because of which the model predicted monkey is there. So this is very, very powerful technique. So because in images like this, it is very clear. We can understand what is there, and for humans, everything is easy. But doing with machines, it is very difficult. That is the challenge we are taking, of course, machine learning. But providing a human interpretable explanation is also difficult. The machine is doing great job, 95-96% of accuracy it is getting, but it cannot explain for humans why it is predicting what it is looking at the image to predict what it is there, right? So this is a very active research. So because it is of high value, right? For example, lot of research is already happening in driverless cars, and I'm pretty sure the companies would love to deploy driverless cars, right? For example, Uber is experimenting already in US. In specific setups, they are trying to do testing.
I have this
But
plan
you
of
have to
eventually
understand, we
getting
know as
married and
humans what decisions we will take, right? When there is a person, when there's a cat, when there's a dog on the road, when there is lights, traffic lights that are guiding us, we know how to behave. And we can train a model also, but can we make the model to explain why it is taking a particular action? So that is very, very important, and lot of research and lot of money is being put into this research nowadays. And to add to this, some time ago, I don't remember exactly when, maybe a year back or so, when Uber was conducting experiments with driverless cars, it killed a cyclist, who was going on the road, who was crossing the road, right? So it says machine learning is really, it's not up to the mark, right? So it has to be developed, it has to be understood. Now the developers will look into that. So why the model failed to recognize that particular cyclist, right? It is very shocking. So now if they understand it, they will fix it. So only then the model gets better. But that itself is difficult. We cannot really easily understand what made the choice, why the model did not predict there is a human, it has to slow down, because it failed to recognize, it crashed and it killed the person, right? So this is very, very active and happening. So this is how it looks actually. So for input image like this, it will identify the pixels, and we can even, as a map, you can show red means very important, blue means less important. Here also there is a B, and it predicted B, and it identified where the B is there. So it can say because of these pixels, I'm predicting there is a B. So these examples we have already seen. All right. So there are a lot of other similar works also. I have given you the list actually, so you may go through. Yeah, feature reconstruction. It's also very related. What it does is basically when you have the intermediate feature, can we get back the original image? So how well the model can draw the input image, right? So for example, let me show the, yeah, here it will take the input image, it will compute features, layer by layer, it will compute features, and it will come here. Let us say we are at this point. So can we ask the model to go back from here and recreate what the input was, right? So this is also one way to visualize the CNN behavior. So this work is about that. So starting from different intermediate locations, can we recover the input image? Can the model show where it started? Can the model get back the initial image? Yes, to some extent it is possible because there is a lot of information loss that is happening. All the redundant information, less informative information is being lost. So because of that, we don't see the complete picture, but we do see a good decent amount of information. So this also is one way to explain what it is looking at, what it is thinking is not important. For example, the predominant pattern here is the dome, right? So maybe what this model is saying is, I am relying strongly on this dome. The other details like the human, the background and the floor, these are not very important. That is why it was not able to recollect. It forgot the less informative information, and it remembered only the important information that is required for classifying the object in the image. So these are all different explanations. So we cannot say what is the right, what is wrong explanation. What is, we can say what is useful, right? Is it really useful? Maybe, yeah. If I want to know what regions it is looking at, this is very useful to me, right? In some other application, the requirement may be different. So based on the requirement only, we can say which explanation is better, which explanation is not better, right? So all those things. All right. So that is what I had for today. But let me just quickly summarize what are the future challenges and directions also in this area. So model transparency is useful in different stages of artificial intelligence evolution, right? So now we are in a high time actually. So we started with humans performing very good and models, the machines performing very poor in the beginning, right? Let us say 1970s or 60s, when we started with AI, models were very poor. The computers themselves were very poor, not in the capacity sense, they were very poor. But we are at a different stage now because we are at a stage where some of the tasks are very easy for computers. For example, object recognition, I said there are 95%, 96% accurate models also, which is very good, right? There are some tasks, for example, um, uh, games like chess, Go, machines are winning the champions, right? You might have seen the experiment by AlphaGo, right? By Google. It had played 3 matches of Go with the world champion. I think it won twice, and the third was a draw, I think. Yeah. So that means some of the tasks machines are better. Machines already demonstrated, yes, yeah, demonstrated better skills than humans. So this is where we may have to learn from the machines. Until now, we are teaching machines how to recognize dog, how to recognize cat, how to understand what we say. It is there. It is called machine learning. So future, we may see machine teaching, because in more and more tasks, machine will outperform the humans. Then we have to learn from the machines, right? For example, the Go, the chess, these are all very strong applications, some strong examples. So we have to understand what patterns it is understanding in the game, how it is playing,